Yo, hey. So, we are masters at derivatives now. We know pretty much all of the rules that we'll need to know. Product rule, quotient rule, chain rule, power rule, trig derivatives, all of that. We know it. So, we're getting into the applications of derivatives now. Now, the first one here is, oh, my bad. Let me start over. We're going to begin looking at what can we use derivatives for when looking at functions, right? This applies to a lot of things: calculus, physics, chemistry, biology, all of that, right? Economics, statistics, applications of derivatives. First, we're going to learn about concavity. Concavity is dealing with, I guess I should also say concavity in like intervals of change. Intervals of change, right? So the title will kind of be different from what's up there, right? They deal with what do derivatives do to functions, what can we interpret about functions when looking at their derivatives. You know, kind of briefly talked about this stuff in the tangent lines video a long time ago. But these two things they deal with, spoiler alert, first and second derivatives of a function. Allow us to make some pretty cool inferences, estimations. We'll be talking about those more. And much further down the line, we'll use derivatives and second derivatives to kind of make even more specific inferences about a function, right? So first of all, I'm going to define what we call a critical number, commonly abbreviated as CN, right? A critical number is, let's say you have a function f of x. F of x, I'm going to draw out to f of x. This is going to be our f of x for the video, right? We'll be in quadrant 1 because that's easiest to explain, right? Ooh, how do I do this? How about we go... Actually, one more. Or not one more. I'll redo this. And then it goes down. Okay, so we're gonna have some important things to look at here. Actually, I'll expand this just out a bit more. Then it goes like that. We're going to talk about a lot of stuff today. First and second derivatives can tell us pretty much all the information we'll need to know about this graph right here, right? And this graph can tell us a lot about second derivatives and first derivatives. Critical number is, let's say this is f of x right here. Critical number is when f prime of x either equals 0 or does not exist. Okay, going back to differentiability, when does your derivative not exist? When is your derivative not continuous, right? Or simply when f prime of x equals 0, right? Now, a critical number is going to indicate some sort of change in the behavior of your function, right? Remember, if f prime of x is greater than 0, what's happening to your function? Well, if your derivative, your rate of change is positive, your function is increasing. Right? So if f prime of x is equal to or greater than 0, f is increasing. Same thing applies. If f of x or f prime of x is less than 0, f is decreasing, right? Your derivative is negative. That means your slope is negative. That means your rate of change is negative. It means your function is decreasing, right? So these are kind of the two big ones when we're talking about first derivatives. What happens when your first derivative is positive? What happens when your first derivative is negative? And the last thing is when f prime of x equals 0 or does not exist, right? So if you have a discontinuity, that's going to basically kind of spotlight the same things as if your derivative equals 0 crosses that x-axis in this case. Sometimes it's a t-axis, remember? Back to our positions, velocities, and accelerations video. Okay, let's draw arrows on this. Cool. So when you have a critical number, you have to think about, okay, now what's happening on either side of your critical number? Because cool, f prime of x equals 0, but what does that mean? That means your slope is equal to 0. Now, I'm looking at this graph. Right here, I can tell that specifically at this spot, f prime of x is equal to 0, right? Now, what that means, and what I can infer from this graph, is here, f prime of x is greater than 0. here on this side of it, it's less than 0, right? The slope goes from positive to negative. As you can see, our function is increasing, and then I'll label this at x equals c here, right? And then it goes to decreasing. So remembering back to our IVT video, you can apply that to derivatives too. If you go from a positive value now to a negative value, and you're continuous on that whole interval, you must have hit 0 somewhere in between there. We can see here that our slope, our tangent line, is in fact equal to 0, right at that x equals c. X equals c is a critical number, right? So kind of an introduction to critical numbers here. So sometimes we see that when we have a critical number, our function is going to have that peak, or down here, a valley, right? It goes from decreasing to increasing. Critical numbers show changes in the behaviors of our function. Increasing to decreasing, decreasing to increasing. Sometimes we go from kind of over here, there's probably a critical number right about here. I drew this graph wrong, but there should be a tangent line there, horizontal tangent. You go from increasing to increasing. Nothing happens. But a graph of f prime of x here would kind of look like that, where you hit the x-axis and then you just bounce right back off. Whereas here at this part, you go from increasing to decreasing. Your critical number here at x equals c, your function would more so look like this, your f prime of x function. You go to 0, you pass it. Now you're negative, right? So that's kind of the basics of critical numbers. We'll go more into depth. This is kind of supposed to be a broad introduction, right? Because there's a lot, I mean a lot, to discuss with behaviors of functions, end behaviors, limit behaviors, derivative behaviors, function behaviors, peaks and valleys, estimations, all of that. Calculus can do so much. Now we're getting to the applications of what derivatives that we spent so long learning about do, right? Derivatives, kind of like little clues as to what our function's doing. So now let's kind of introduce concavity. Concavity is going to be something that is more vague. It's you have to think really far out. You're getting to the kind of confusing territory, right? Confusing territory of what calculus is. You have to kind of make inferences. You have to think, because concavity is going to deal with our second derivative, right? It's kind of wacky to think about what your second derivative is doing to a function of I guess 0th order derivative, no derivative. It's a lot of like thinking, but you'll get used to it, I promise. So concavity is, and I'll give you this cool little analogy soon. It shows the trend of your derivative, right? Yes, your second derivative shows the slope of your first derivative, right? And so it shows the slope of your function. That's a little weird to think about. Concavity is really easy to see, really, really hard to think about. We have two ways of describing concavity. Concave up and concave down. And we see both of them on this function here. A little roughly, because I'm not the best drawer, but concave up is going to look something like this. Concave up looks like a cup, right? Concave down looks like a frown, right? That's concave down, that's concave up, right? So, and this is kind of just a general behavior. Concavity can look like a lot of different things, but here you see what's happening. Our derivative is decreasing. If we go all the way back to this f prime graph that I tried to draw at that critical number x equals c, we saw that it was decreasing because we went from positive derivative to a negative derivative, right? So the whole time the slope of that derivative is negative, which means our second derivative is negative, which means we're actually concave down. Concave down is when f double prime of x is less than 0. And concave up is going to happen when f double prime of x is greater than 0, right? And now, lastly, I'll draw it up here. When f double prime of x equals 0 or does not exist, very, very similar to critical numbers, you have what we call a candidate for an inflection point, commonly abbreviated as CAND. C-A-N-D. Candidate for inflection point. Now, an inflection point is when we go from concave up to concave down, or concave down to concave up. It's a candidate, doesn't mean there's always going to be an inflection point there. Sometimes, again, your second derivative kind of hits that, bounces up, and then you just You stay concave up or you stay concave down, right? So you kind of have to skip a derivative when thinking about concavity. If you want to think about, okay, what's happening to your derivative in the same way as you can think about how your derivative affects your function, how does your second derivative affect your derivative, think about that too. It's perfectly fine. But you just have to know that concavity looks different than slope, than intervals of increasing or decreasing. Because here, I could tell it's increasing and decreasing, but in this entire interval, it's concave down, right? Your derivative is increasing. Generally, concave down is going to look like, you're starting off, going up pretty high, and then you level off, right? And then concave up, kind of opposite. It looks like your slope is kind of shallow at first, and then, whoa, you go up like that, okay? So here, we're going to be concave up. Does that kind of make sense? Our derivative is initially very, very negative, and then, we're going positive, 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 positive. See, this is kind of like a tangent line. Ooh, and then we go up, right? So our derivative is increasing. Our function is kind of blooming out, whereas concave down, we're kind of trying to, we're slowing down. We're hitting the brakes with our derivative. We're hitting the brakes with our function. Whoop. And then down here, like going down a huge roller coaster, whoop, right? Perfect analogy. You're going up the roller coaster, you're kind of slowing down, and then all of a sudden, whee, right? Okay, you're going. So you get it. Now over here is kind of a weird area because we have this point right here, and I tried to draw it. Bear with me here. This is an inflection point. I can tell just by looking at it. This area up here is CC down, concave down. This area, roughly here, is concave up. There's a lot written on the board here right now. There's a lot going on. Remember, there's a lot with derivatives. This is why I said it kind of gets confusing and complicated. You have to think about a lot of things at once. But generally, especially if you're in like a class, right? You'll only be asked about one of these at a time, generally, or in kind of steps. So usually it doesn't get this weird and complicated and messy, right? I can tell here that our derivative starts kind of shallow. It's increasing. Then, whoa, we're going way up. Right? Almost vertical. We have a vertical tangent here, essentially, right? And then, suddenly, our derivative is decreasing as we approach this valley, or this peak here, right? So, generally, as you go from valleys, low areas, to peaks, you're going to have shifting concavity. Same thing here. I tried to draw a candidate for an inflection point right there, where we go from concave down, and there has to be a point where we go from concave down to concave up. We can't just shift from it. Actually, we can. That'd be a discontinuity. Remember, your second derivative also can just not exist at a point. That is possible, but generally in calculus, remember, calculus is the study of continuous change. We like continuous functions. Continuous functions, very applicable to real life. Discontinuous functions, not very applicable to real life. Got really dark all of a sudden. So that's really kind of the broad introduction with concavity. Concave down looks like a frown, concave up looks like a cup. You'll never forget that, just like you'll never forget low D high minus high D low, draw the line, square the low, or left D right plus right D left. Never forget them, right? I'll let you look at all that for a second. The next video we'll probably do some more kind of examples with these, spotting these on graphs, drawing graphs given information about concavity, drawing graphs given information about your slope. I could not show you this graph right now, and if I told you at x equals 0, your function is decreasing, at x equals 2, your function is increasing, what could x equals 1 be? And you could tell me, it could be a critical number, right? Because your derivative goes from negative to positive, your function goes from decreasing to increasing, right? But starting off, we'll be looking more at graphs. All right, concavity. First look into the applications of derivatives, right? These things do a lot. We have a lot ahead of us. Multiple videos discussing just these two topics, really, how first and second derivatives affect functions. Once you get to third derivatives and up, kind of is weird. It's really, really difficult to think about what those do to your graphs and what they do to your functions. So we don't generally deal with third and fourth and beyond derivatives as much as we deal with first and second derivatives, because those derivatives really, really do show impact on our functions. So Anyway, thank you very much for joining me for this confusing, kind of messy video. Goodbye, class.